Hello, I'm Dr. Hongchao from the China University of Ming and Technology. I would like to introduce our team's research title, UWB sensor-based NLOS or NLOS localization. It's support vector machine learning. My introduce will be divided into three parts: background, system, and experiment. We use UWB ranging technology based on signal time of flight by recording Paul frames, response frame, and final stream transmission and reception time between different enters. We calculate the signal time of flight using the formulas and further determine its distance. When the number of the enters is more than 3, we use the least squared method to estimate the coordinate of unknown point. Distance measurement error significantly affect the localization accuracy. So, NLOS transmission is common in complex indoor environment and with objects like walls, doors. Therefore, recognizing and mitigating NLOS ranging errors is crucial for prediction and localization accuracy. Our approach to identify NLOS involves features acquisition and classification. Most exciting features are based on the mathematical information of the channel response, channel express response, which is limited and cannot capture the key point. Our team's research divides the computer communication CIR into 3 types, 3 stages. The first stage is the environment noise stage, and the second stage is the first pass arrival stage, with a sharp increase in CIR due to the UWB signal arrival. The third stage is the multi-pass signals. We propose the first parameter we propose is the first coarse number, which counts the number of the abnormal high energy CIR in the environment in the noise stage. In NLOS, this feature likes to be 0, and as shown in the left graph. In NLOS, this feature is include high energy UWB signals. It's more than 0. It is 8 in the right paragraph. So the threshold for this parameter is set at 60% of the NLOS of the environment noise level. The second feature is the first pass errors. We use a small constant threshold to compute with the environment noise level to calculate the first pass signal, and calculate the difference between the new first pass time and the UWB report first time. In NLOS it's tiny and due to the NLOS stable, and in NLOS it's due to the weakened true first pass signal, it is more than NLOS. The third one is the first pass power level distance error. We create a function that releases the first pass power level to the actual distance based on a signal attitude model to offset the additional attenuation of the signal by obstruct under the same first pass power level. The actual distance of the NLOS is longer than that of the NLOS. So the value of the parameter in NLOS is much higher than the NLOS due to the positive random error. To further capture the hidden channel information within the features, we introduce the conception of physiological. We assign a special value to the feature to indicate their possibility from the alongside environment. This can enhance the robustness of the features and the recognition algorithms. In the offline, we construct the membership functions through data normalization, fuzzy statistics, and function simulation. For feature vectors, we introduce the mean factor method and the central method to determine its fitness. The right side shows the membership function of the 3 new features. The diagram shows our overall structure. In the offline, we construct the membership function. In the online, we begin by pre-classifying the date, use the dynamic threshold compression, and then combine physiological with SVM to achieve the final classification result. The dynamic threshold compression has 2 steps, with the first step being threshold utilization. We select 6 features, include the new 3 one. For data pre-classification. First, we remove the first and last 3% of the sorted offline dataset for each feature. We use the value as the 90% of the dataset for utilization, with the contrast that it cannot exceed the data threshold provided in the offline document. After data process through SVM and results in the final classification, we update the threshold every 330 alongside data. In the channel result for 6 features in dynamic threshold compression, and either alongside or non-alongside, if the data do not require further classify and are directly labeled with the corresponding channel result. For the remaining data, we consider 3 cases, and for each case, we provide corresponding feature combination. In the range error mitigation, we classify ranging errors into 2 types. For alongside data, forecast number is 0 is equal to its features, so it do not need to be mitigated. For the alongside data with first number more than zero, which include the misclassified NLOS state and some NLOS state with possible errors. We need to try them. For NLOS data, we also divide it into 2 parts. The first one is the coarse number is 0. It's like because the true first pass signal is significantly weakened. Well, the remaining data is unequal features. So we calculated the error correction based on the timing of the first abnormal CIR in the environment noise stage and the inverse stage of the first pass signals RNG. This is our experiment environment. In the left static experiment, object includes wall, human, and mixed object. Mixed object refer to the presence of various objects between anchors, including wall, human, table, chairs, and animal. In right static experiment, object consist of human and glass. The table 3 is the static real distance result. The left paragraph compares the accuracy of the signal features, including both existing features and our new features. It shows that the new features have higher accuracy and greater responsiveness in various environments, with accuracy reach up to the 82%. The NLOS recognition also provided by our teams of outperforming exciting research in terms of accuracy and recall NLOS and recall NLOS. Unlikely existing research which only correct NLOS data, our team additional corrects on NLOS data. Table 5 shows the correcting NLOS errors with improvement of more than 40%. As shown in table 6, NLOS error after mitigation is with an average reduction of 44% and 46% in standard deviation and root mean square errors. The communication distribution function performance of mitigation alongside is more than 90% for random error of its half meter in all sensors, outperforming the raw alongside. In alongside, more than 90% of data of the is less than 2 meters. As shown in the figure 13, the max errors for alongside and non-alongside are reduced by 20 centimeters and 1.8 meters respectively compared to the original dataset. Our mitigation method perform better than the least square SVM and KN. This is our dynamic experiment with obstacles such as human, glass, and wall. The mean and the max errors are reduced by more than 50%, and the standard deviation is reduced by 55%. After mitigation, the trajectory is more close to the reference. So it's our conclusion. We propose 3 new features and one of the proposed features always has the best accuracy in this 5 experiment. And the remaining 2 are with approximately 10% performance from the best achieved as compared to the exciting CP. The mean alongside or non-alongside accuracy in various testing center is 93.27%, and the alongside and the non-alongside recall are more than 94% and 92%. In the running error mitigation, the proposed approach leverages a new CP to classify and correct the running error in both alongside and non-alongside. The average errors for the corrected alongside and alongside are less than 1 meter and 10 centimeters, resulting in more than 90% of high precision random accuracy. The system can improve the multi-dynamic precision accuracy by 63% with a mean error of about 10 centimeters. In the future, our team is working on explore higher precision channel characters and channel identification algorithms that can combine artificial features and CIR sequence, refine alongside and non-alongside errors, models establish distance measurements result recall machine and enhance UWB data localization. And the last is the intelligent fusion stage for UWB and non-wire signal position also to further mitigate the impact of NLOS for failures. Thank you for your attention.